Lesson 11.1, Part A, Defining and Using Sequences. A sequence is a function whose domain are integers, so you can only plug in numbers 1, 2, 3, 4, 5, or negative numbers, but no decimals, no fractions. And it gives you a list of numbers that follow some sort of rule. So it's like a function, just no decimals in the inputs. You can have decimals as the output, but not as the input. 2, 4, 6, 8 is a sequence. It ends, so we say it's a finite sequence. 2, 4, 6, 8, 10, dot, 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 means it continues forever, so it is an infinite sequence. An example of a rule, so the rule for this one is an equals 2 to the n. Alright, so n has replaced x. N is usually the variable for integers, so we use n. And an is like f of x or y. It's closer to f of x because a is our function and n is the variable. But it's also like y. So our domain, the x's, is now n's, and it's the term's location. It's the first number, second number, third number, fourth number. The range, the an, is the value, 2, 4, 6, 8, etc. So let's try this example. Write the first 4 terms of this sequence. All right, well, the first one, we're just going to plug in a 1. Which gets me 1/2 minus 3. That's negative 5 halves. A2, plug in a 2. That would give you 1 minus 3 is negative 2. A3, plug in a 3 for the n. So it gives us 3 halves minus 3, which is negative 3 halves. And A4, plug in a 4 for the n, so it's a half of 4 minus 3. 2 minus 3 is negative 1. Why don't you pause this and try number 5. F of n, see now they've changed it functional notation, but still the same thing. This is like an, whatever. So your first one is a to the 4 to the 0, which is 1. Your second one would be 4 to the 2 minus 1, which is 4 to the first, which is 4. F of 3 would be 4 to the 3 minus 1, which is 4 squared, which is 16. And f of 4 is 4 to the 4 minus 1, which is 4 cubed, which is 64. All right, writing rules for the sequence. So if you know the sequence, how do you come up with the rule? Well, there's no hard and set way. So what we'll do is we'll look for patterns. Maybe do a little guessing and checking. If there's fractions, you look at the top and the bottom separately. For example, 2 over 5, 2 over 25. All right, so let's look at the top and bottom separately. So the top, I'm thinking we can easily see is a 2. Because there's a 2 on top. The bottom one, you can look, you can see we're multiplying by 5, or maybe this is 5 to the first, 5 to the second, 5 cubed, 5 to the fourth. Well, how am I going to write that? Well, the first one, n is 1, and then n is 2, then n is 3, and n is 4. So notice the value of n is the same as the exponent, so it could just be 5 to the n. Why don't you try number 13? All right, this one's a little more difficult. Notice you have a pattern of adding 0.7. So our first number is simply 3.1. Our second number, the 3.8, is 3.1 plus 0.7. The third number is 3.1 plus 2 times 0.7. And our third number is the 3.1 plus, well, there's three of them now, 3.7. So this would be like 1 times 0.7 and 0 times 0.7. So that looks like it's going to be 3.1 plus, that's the number that's changing. So for the first one, where n is 1, that number is 0. For the second one, where n is 2, that number is 1. So it's 1 less than whatever n is. So it'll be n minus 1, and then the 0.7. Well, we could distribute that. 0.7n minus 0.7. Combine like terms, 3.1 minus 0.7 is 2.4, and this is an. Nice, finding a pattern. To graph sequences, remember n is like the x and an is like the y. However, the graph will be dots. We don't connect the dots, because if you connect the dots, you're saying that you have values between like 0 and 1. So it just looks like this. It's just dots. If you were to connect them here, you're saying, oh, well, we have a value at 0.5 and 0.75. But you don't. You have just the integer values.